Good afternoon, dear colleagues. We are now about to open our last plenary session of this event. This plenary session will be given, this plenary talk will be given by an outstanding speaker, Roger Brockett. And I need to say a few words about Roger Brockett. Roger has a lot of awards. You can find the list in your program book. I mentioned already that Roger is one of four awardees of the IEEE Control System Awards, very distinguished award. And we are happy to have Roger here. And for people not in control, a sign of good reputation is that he is affiliated with Harvard University. But in addition to this, he has a lot of other other important achievements and known to all the control community. And as for myself, I was not very familiar with Roger personally until 2 years ago, actually 1 year and a half, when he sent me email and suggested to make a joint lecture course on control related to physics. I was very excited because this area on the boundary between physics and control is my favorite area for several years, and I was thinking that nobody is interested much in this area among control community. And when I got such email from Roger, I was really, how to say, excited about, it was a sign of evaluation of importance of this area. And I know that the results, the methods Roger used and suggested, introduced into our science are closely, how to say, discovering interconnection between these two great sciences, physics and mathematics. So, and geometric control, the area which he pioneered, is also a good example of such a interaction between mathematical techniques and physical insights. So let me stop at this time and invite Roger to make a lecture. Please.
Thank you for the generous introduction. It is traditional for people to say how beautiful Leningrad is, or St. Petersburg, and I'm happy to acknowledge that St. Petersburg is in fact very beautiful, and how grateful they are to be asked to be here, and I am grateful to be asked to be here. So you can more or less assume that all the things that should be said, I agree with. So, and now I want to go on. All right, so unlike some talks, I'm going to talk about a single problem, but it involves many steps. And so this puts a bit of a burden on the audience. First of all, they have to decide what the problems we're talking about in the first place. And then there will be a number of elements for it, and if they miss any one of those elements, it's likely to put them to sleep. So I'm going to try to be as dynamic as our earlier speakers have been to try to ward off sleepiness on your part. So, a problem with a great tradition is Huygens and his clocks. And I was appalled, I guess is what I could say, No. It must be there. To learn about this picture, I had always imagined that Huygens had put the clocks on the wall, and apparently he was a sickly person by spells, and that he was lying there in bed unable to do much. But instead, now, here's a picture from his notebook of a couple of chairs with something stretched across and two pendulum clocks hanging from that. And what he was amused to see was that after some time, the clocks would synchronize. And what I would like to do is to talk about that problem. Now, I'm going to argue that in spite of the messiness of that picture, that there are certain intrinsic things that will be difficult to argue against that have to go into the solution of that problem. So, we start now gathering some information as if we were gathering food for supper. First thing I want to remind you of is the idea of integral control. Now, I know you all know what integral control is. I just want to say it my way. Great example here. Water supply comes in, dumps into a vessel. You have a pivot here. The float goes up, turns off the water, so forth. In effect, the height of the water integrates the water flow. It accumulates it over time. And this results in a system in which there is no steady state error. It's a very simple system and gives you not a small steady state error, it gives you no steady state error. Okay, so feedback, I'm going to want to distinguish between proportional feedback, which you know about, and integral feedback, which I'm going to expand, I hope, expand your working feeling about what integral control is. And the idea that this is important in this problem. Okay, first, a main point is that integral control is not necessarily linear. Integral control has a nice interpretation in terms of differential geometry. There's been some talk today about potential functions and so forth. The integral control will involve something that are the antithesis of integral functions, which unfortunately goes by the name of non-integrable, but non-integrable has too many meanings.
You might use the microphone.
Oh, I'm sorry. Oh boy. Okay. Now, in terms of a picture, what you might think of is taking this trajectory and converting it into a trajectory like this. Now, what do I mean by that? Suppose you have one clock going at a certain frequency and the other clock going at a frequency that's close but not exactly it. So then you sketch out the paths of the pendulum and you see this beautiful geometric pattern developing, but it doesn't repeat itself because the frequencies are not integral related. The mechanism that needs to be explained, represented by this arrow here, that takes this picture and converts it into a picture in which the trajectories all approach something which is synchronized. Okay, so I'm going to say what doesn't work, first of all. So, x double dot plus qx equals 0. Standard oscillator, I want you to think about this happening in n dimensions. So, Q would be a n by n symmetric matrix, and it would be derivable from a potential function. So for the clock problem, it's some version of gravity together with a circular constraint. If the eigenvalues of Q are not the same, Huygens and the clocks, okay, the clocks were maybe made by different clockmakers, or even if they were made by the same one, they wouldn't be able to do it twice exactly the same way. So the natural frequencies of the clocks are represented by the eigenvalues of Q, and the question is, what kind of coupling mechanism could possibly result in bringing together these eigenvalues? I want to argue that you cannot postulate some function x and x dot which will give synchronization unless you magically give F the knowledge of how they were different in the first place. And that really doesn't explain anything. So we reject that. And I say that problem has no solution unless we let F depend on Q, and that is unrealistic. Okay, a better starting point is we want to allow dynamic coupling. And so we add to this set of equations an equation for a variable I'm calling z. Now, where would z have its physical embodiment? Well, if you think about the rack that held the clocks, or if you think about the clocks being on a wall, and you think about the dynamics of the wall, you can imagine that z is in fact capturing the essential parts of the dynamics of the coupling between the two clocks. And I want to argue and make you believe, insofar as I can, that even though the coupling is poorly described, even though it's undoubtedly messy, so forth and so on, that you can legitimately ask the question, well, this didn't seem to depend on the strength of the coupling. If you take the clocks and put them farther apart on the wall, they still synchronize. So you want an effect that doesn't depend critically on the strength of the coupling. And in fact, you can imagine that you would want to allow for the possibility that the coupling was as weak as it can be. So you cannot achieve synchronization by means of linear coupling. I think that's intuitive. It wouldn't be hard to show that, but I'm not going to. So that means that what you would like is to know what are the lowest degree terms that would possibly explain the synchronization of the clock. And that's a question that I think will give a satisfactory answer to. Okay. So, this is saying what I had just said. The synchronization seems to be independent of the coupling strength. Originally unequal periods get equalized. It does not fix the relative amplitudes of the clock. So we're not trying to solve the equal amplitude problem. We're just trying to make them synchronous. Okay, the answer is going to involve three kinds of ideas that are actually quite distinct. There's a linear algebra problem here that relates to convexity, we just heard about. There's a differential geometry problem here that involves the non-existence of potentials. And there's the control theory idea of nonlinear but integral feedback. Okay. So I told you this story before, is that Huygens did not observe that the clocks synchronized instantly. And in fact, he didn't observe that they depended critically on some level of interaction. But what he did observe is that if you waited long enough, they synchronized. So you're looking for some effect that builds up over time as the integral of something or other. And in fact, you're substituting for the unknown gain, you're substituting the length of time that it takes for the error signal to build up. Eventually it gets there, but not right away. Okay, just as it takes time for the float valve problem to solve. Okay, so now I'm going to talk about a math problem. And this may be known to some of you or may not. A real symmetric matrix, Q. I'm going to do something with Q that may seem very strange. It's not about me. This is a result of Isaiah Schur and Alfred Horn. So Horn's part is 60 years old, and Schur's part is 110. So you take the eigenvalues of a n by n matrix, and you list them. But the eigenvalues are not ordered in any natural way. So you list them in all possible orders. And that gives you n factorial vectors in n space. Not what we ordinarily do in linear algebra, but it's not illegal either. Here's a picture. I have, say, a 3 by 3 matrix, 3 eigenvalues. There's 3 factorial ways to list them. You get 6 vectors in 3 space. You take the convex hull of those vectors, and if you ask the right question, that convex hull tells you something interesting, namely the diagonals, the possible diagonals of a matrix of those eigenvalues has to lie in this convex hull. And even more so, and this was Horn's contribution, is that any point in this convex hull is a possible diagonal for a symmetric matrix with the given eigenvalues. It may not solve all your problems, but it's certainly something that's so pretty that it's worth knowing about. Anyway, what I want to do is I want to use that result to help us with Huygens. So, this is a theorem that is original with me, but I don't think I'll get very much credit for it. I asked the question, if I add a skew-symmetric matrix to Q, where can I put the eigenvalues of this combination? For example, can I add a skew-symmetric matrix to an arbitrary symmetric matrix and place the eigenvalues in some particular set? So what I want to show is, we'll see, is that by adding a skew-symmetric matrix Z to a symmetric matrix, I can place the eigenvalues anywhere in this same convex hull. That is to say, through Z, we can place the eigenvalues there. And in particular, I can put them all in the same spot. Why do I want to do that? I want to do that because I want to synchronize. So that means I would like to pick Z in such a way as to make all those eigenvalues the same. Okay, how do you prove that? Well, it's not very hard. You use the fact I just told you about the Schur-Horn polytope. And now you might imagine that Q itself was generic, and you add Z to it in such a way as to make it upper triangular or lower triangular, it doesn't matter. So what you can do is you can take a symmetric matrix, add a skew symmetric matrix to it to make it upper or lower triangular. If it's upper triangular, then the eigenvalues are on the diagonal. But the diagonals are already known, the possible diagonals are already known to us by Schur-Horn. So we just take an orthogonal matrix that puts the eigenvalues we want on the diagonal, which is possible by Schur-Horn. Then we choose Z to make the sum lower triangular or upper triangular. And that solves this little lemma. There's a story to be said about the elementary divisors of Z plus Q, but I'm going to skip over that for the interest of time. Okay, so just to give the conceptual picture here, or try to, the theorem goes from eigenvalues of Q to diagonals via Schur-Horn back to eigenvalues of Z plus Q. Okay, and if those of you who like to think about pole placement problems or eigenvalue placement problems, you can think about Schur-Horn as being diagonal placement problem, where you ask yourself, can I place the diagonals of a matrix in a certain way? Okay. You want to think about that some more? Is that okay? An example. Start off with 10 and 8. Add the skew symmetric matrix here. There's a particular value of Z that makes both the eigenvalues 9. You're not going to change the trace of the matrix by means of an off diagonal, of course. And so the only choice is to have it be the average value of the trace, that is to say, the trace over n. Okay, good. We've had enough of that. How are we going to use this fact? Well, what I'd like to do is to describe a feedback solution that generates Z for you. So this is what we need, is to find a method to produce Z that equalizes the eigenvalues. Okay. Now, just to give you something concrete. This is sort of slightly out of order, but just to, so I don't want to lose people, I don't want you to lose faith in the story I'm telling. So suppose we take two coupled second order oscillators with a little bit of amplitude fixing here in the middle. This is unstable for small x, stable for large x. These would individually, they oscillate. We didn't have that term. This one would oscillate at a certain frequency. This would oscillate at a different frequency. I've chosen matter so that the sum of those trace is 1, just so we don't have to worry about numbers. Okay, but I want to now choose Z. So you can see, you could see if it weren't for this line across here. This is Z times Y, this is minus Z times X. So there's a skew symmetric matrix here being added to what is basically X double dot plus QX. Okay, and I want to choose Z. And what I don't care about is I don't care about how long it takes me to achieve synchronization. I just want to be sure that I'll get there eventually. So here's another picture of it. You have an oscillator with one frequency, clock 1, clock 2. And you want some gadget here that will have a look at these signals and produce a corrective term that will make everything synchronous. All right. Okay. Now, I want to take on, maybe this is the part that will seem the most unusual to you, and that is, I want to analyze all the possibilities for the correction term. Now, when a person says, I want to analyze all the possibilities, you're immediately skeptical, and ought to be, of course. Critical thinking shouldn't take a holiday. But have a look, just for the sake of concreteness. I've got variables here, x and y, and x derivatives and y derivatives with respect to time. And I ask you, since I want to look at the lowest order terms possible that will account for the synchronization, naturally I want to look at quadratics. So I ask of these things, which of these quadratic functions, or how can I characterize those quadratic functions, which in fact are capable of building up over time, with x and y being bounded, because they're bounded by the energy constraint of the system. But there's some of these terms whose integrals are not bounded. What are those candidates? Well, not x dot, because that integrates to x squared, and if x is bounded, then x squared is bounded. But on the other hand, if you take x y dot minus y x dot, that's not the derivative of anything. That's a so-called one form that is not exact. So I could use x y dot minus y x dot, and it's the integral, the time integral of that, and I could get a signal that reflected what? Well, if you think about the derivative of an angle, this is something like that, except, if you remember calculus class, x y dot minus y x dot is a line integral that gives you area. So this then allows you to measure the area swept out by the x and the y trajectory as time goes on. And if those things are not synchronous, that area will build up to infinity and generate a signal, no matter how small the coefficient is in front of these terms when you actually use it. It'll build up to infinity eventually, and you'll get that to work with. So here's saying that I described it as if it were 2 dimensions. I'll say something in n dimensions. Things work similarly if you have a curve in n dimensions, and you project that curve onto the various 2-dimensional planes that are present, you'll get n times n minus 1 over 2 possible projected areas. And in 2 dimensions, you get just 1. And it's familiar listed you figure that many have seen as undergraduates. Okay, so the corrective signal, if we take it to be, if we take the basic response of the pendulum to be sinusoidal, and we ask ourselves, what does x y dot minus y x dot give us? Well, it gives us the phase angle between those two. And if we do it in n dimensions, it gives us n times n minus 1 over 2 phase angles. And the point of it is that the integral of these things builds up without bound unless the signals are synchronized. So if they're synchronized, t goes to 0, and you just get a straight line, and the area associated with that is nothing. Okay, now let's see if we can put these pieces together. The key thing, remember now, and in some sense the only thing we have to worry about from this point on, is how do we choose the dynamics for z that will force the eigenvalues of this together? Does that sound easy, or does that sound hard? Okay. If x is two-dimensional, we seek a solution with z equals constant. That will then do the right thing by those eigenvalues. Okay, now I'm actually going to postulate a particular choice for this z. Now I told you before, I asked you to believe before, that the solution to this problem was essentially unique. In spite of the messiness and all the unanswered questions about what the backplane between the models might look like, how would I talk about that? Well, you can ask yourself, is there something special about this x y dot minus y x dot thing that I put up there? So that suggests a problem that has a nice answer. Even if you allow arbitrarily high derivatives, you can ask yourself, what are all the possible quadratic, non-integrable, area-like things that exist? So you can evaluate that, and it turns out that in 2 dimensions, anything that isn't proportional to this is out. So this is one more caveat. You don't expect to find any help in synchronization by looking at a function of x alone or looking at a function of y alone. X is going to talk to y, y is going to talk to x, if you're going to synchronize the oscillations between x and y. So, the statement I just said was wrong, as I said it, because things like x dot squared and so forth would be okay. But if you look at things that are functions of both x and y, this area term that I've described is essentially unique. And so here's this choice of z that works. So we're going to let z act on, well, now I'm writing equations as if they were in n dimensions because that's more general. So you look at generating these multiple areas here that give us a skew-symmetric matrix. You put the skew-symmetric matrix in there. You look at this then coupled equation, and what happens? Well, if the eigenvalues of Q are not initially equal, Z will build up according to this equation to make the eigenvalues equal. X will then be operating in an eigenstate with just one frequency, and Z will go to be stable at that constant that you have described there. So that is a little bit too glib or simplistic because I have ignored the effect of the damping term. Now, what I would have said would be just fine if, in fact, this term did not produce any phase change in the signals. But it does. It can produce phase change. But this term can be arbitrarily small, and that's a part of the problem which isn't very much fun. So I'm going to ask your indulgence and not talk about that. It's a small effect. It's there. It's annoying. I don't want to talk about it. Okay. So, point of it is that area coupling will synchronize. It doesn't matter how big the coefficient in front of this term is because it builds up over time. So a small value of the coefficient here will be compensated for by just waiting for a longer time. You can look at this issue from a completely classical point of view and write down a Heaviside-like description of the situation. It tells you things that weren't quite obvious from the description I've given so far, but it's also has some limitations, and it would be very difficult to try to design something or discover a phenomenon from that point of view. Okay, so you think I've asked you to take on faith quite a lot, and that's true. So sometimes simulation convinces people where nothing else suffices. Here's an example of something which has close but not exactly the same. After all, Huygens' clockmaker didn't screw up entirely. I mean, the clocks were pretty close before he started. So it's not so terrible to look at the case with small numbers like that. Okay, and the Z, which would ordinarily be written as a 2 by 2 matrix, but that takes too much space on the screen. So I just wrote, if you like, the 1-2 element of the skew-symmetric matrix Z. And so otherwise these equations are just exactly what I described. And now here's the position of one clock, position of the other clock. You start off with some not synchronized situation, and what do you end up with? You end up, the story of synchronization is that the blue line doesn't cover the whole square. The point of it is the blue line stabilizes to this dark blue picture, which indicates an oscillation with a certain phase difference between the signals, and the phase difference is stable with time after it reaches its equilibrium. That phase difference generates the Z that enables the synchronization. If you like to see transient response of Z, what it is it comes down and it settles down to what it is you want. Now, another way to talk about this, and a way that I think actually conveys a certain amount of intuition, is that there's a number of things that work in the world by taking a sinusoid or a couple of sinusoids and rectifying them, AC to DC. Now, people often think about rectification as being done by something discontinuous, like a bridge circuit of some kind with diodes. That's absolutely not necessary. What the right way to think, well, a smooth way to think about rectification is to think about it as a differential one form which is not closed. And that's exactly the building blocks for integral action which is not necessarily linear. One forms that are not closed, like our x y dot minus y x dot. Okay. I don't feel obliged to keep you until the announced time of the closing party. It's okay, right? No, you got the sign backwards. Question. Just doing not every time. Yes, good. I've given you a result about eigenvalue placement. If I didn't tell you anything else, I'd be happy to give the talk. Add a skew-symmetric matrix to symmetric matrix. Where can you put the eigenvalues if they're real? I told you. We have given an argument supporting the claim that Huygens synchronization must involve integral control, and that it can't involve linear integral control. Why did it have to involve linear control? Because the coupling was not something of fixed size. It would work even if the coupling was extremely small. So if you have some small effect, what can you do? You have to let it build up over time. Integral action. I didn't make as big a deal about the classification of non-integral terms as I would ordinarily have done. It's a beautiful story, but I'm not going to talk about it. We've given you a way to think about synchronization. I don't know whether it's any good for your problems, David, or not. I'm not claiming it is. I just think this is a nice little piece of control, mathematics, and history that bears knowing. Okay. There isn't nearly infinite literature on synchronization because this problem of Huygens has attracted so much attention, but also because communication systems require synchronization, power systems require synchronization, and so forth and so on. So I'm not giving you a literature survey here. I'm telling you the elements that went into this talk. And there's a paper called Synchronization Without Periodicity. Without periodicity, why? Well, because I didn't say anything about whether the amplitudes were constant and didn't play any role in what I was talking about. There's a paper that I glossed over here about, which you could also interpret as saying, if I give you x dot equals ax plus bu in n dimensions, m inputs, and I give you the additional equations, which describe z dot equal, on the right-hand side, the entire set of quadratics that you could make out of x. So think xx transpose, that entire n-dimensional set, but it isn't n dimensions because symmetry is n times n plus 1 over 2. Which of those are controllable independently? That's a nice little problem, and it has a nice answer. And then more generally, the equations that you end up with here are very much part of a larger question of pattern generation, and the essence of the problems talked about here, if you want to put it in its most St. Petersburg-like terms. So we all saw Catherine's statue riding the horse, and if you think about horses galloping and synchronization of the motion of the muscles of the horse, well, so the question is, how do you synchronize a system as complicated as a horse or a human being with a couple hundred degrees of freedom? Are there some general principles about synchronization that could be applied to those biological problems? And most recently, I've been working on some problems in cell dynamics, which require a level of synchronization that's also interesting. Okay, thank you for your attention.
Questions, please.
Is it possible to control frequency of synchronization?
Well, in this, what would you have in mind?
You have periodic trajectory.
Yeah.
Essentially, two oscillators approximate this periodic trajectory, correct?
Yeah.
Okay, so I mean that can you create new periodic trajectory using feedback?
Yeah, I think you can. So in effect, the damping terms do that. So they create the energy balance that determines the size of the amplitude, size of the oscillation, and that's a much easier problem.
More questions, please? May I ask a historical question? That's me, Roger. I might. Yes. So there is a long story among physicists about this Huygens manuscript. Actually, he wrote about synchronization, as you told, observing these pendulum clocks. And what he described, he always described the anti-phase synchronization and never described the in-phase synchronization. And there were several papers published by physicists and maybe by some mathematicians also, trying to explain why he did not observe in-phase synchronization. Can any explanation be produced using your approach for this problem?
Epsilon. I can add epsilon to that question. Namely, for these equations, the z variable can be thought of as living on a circle. And so for topological reasons, there has to be two equilibria. And in fact, for these equations, there are four, two of them stable, two of them unstable. So the antiphase solution would also satisfy the equations and satisfy them in an asymptotically stable, locally asymptotically stable way. But I think the question you raise is more subtle than that, and therefore that's only a piece of an answer.
Please, we have some time for a few questions more. What they are thinking. While audience is thinking, may I ask one more question? Because this problem is very interesting for me, actually. We are working in synchronization with my colleagues, with Henk Niemeyer, starting with Blechman in 1996, and there were many problems we tried to solve. Not all of them are solved yet. So when we are speaking about synchronization, trying to control synchronization, to make some interconnection between pendulums, ensuring synchronization, we are thinking in terms of energy. We try to, if we have two pendulums, if they have different level of energy each, they will not be synchronized because they are nonlinear for different value of energy. Natural oscillations frequency will be different. So we will first need to equalize energies. And this can be done with small control. And then you need to achieve synchronization. And we do not know answer if it is possible to achieve by small control. In your method, is it possible to achieve with arbitrary small control if there is no friction?
Well, if you allow integral action.
Okay.
So you put an arbitrarily small nonlinearity and then you just integrate and wait.
Yes. I get it.
Now, I think that's the beauty of this insight about Huygens, is that it solves the question of who could possibly model that brick wall or whatever it is that the clocks were hanging on. And the point of it is, if you take the attitude, I only care about the lowest order terms that could possibly explain it, and then I allow you to integrate those, you can do it.
So integral is powerful.
Integral control is powerful, yes. Just like the filling the cows.
Thank you. Are there any other questions? If not, let us thank our speaker.